So for the introduction, an orifice is a small opening provided on the side or at the bottom of a tank through which fluid flows. In engineering application, orifices are used to measure flow rate or control the discharge of fluid in pipeline and tanks. The flow through an orifice is influenced by energy losses due to contraction and friction. To understand this effect, it is important to study the behavior of fluid passing through an orifice. This experiment focuses on investigating this flow characteristic and the related coefficient. Next is the objective of this experiment. First, to determine the coefficient of discharge, coefficient of velocity, and coefficient of contraction for water flowing through an orifice. Next is to measure the jet trajectory using probes and calculate the actual velocity of the water jet. And last, to get the actual velocity and flow rate, then calculate the Bernoulli equation and to study the effect of water head on these parameters.
Problem statement. First, discrepancy between theoretical and actual flow. Actual orifice flow differs from theory due to losses from viscosity, turbulence, and jet contraction. This experiment determines the discharge coefficient CD to correct theoretical values. Second, accuracy of orifice flow measurements. Orifices are widely used for flow measurements in hydraulic structures and pipelines. Accurate discharge and velocity coefficients must be obtained experimentally for reliable readings. Third, effect of orifice geometry and head on flow. Flow rate is affected by orifice shape and water head. This experiment studies these factors to support better hydraulic design and analysis.
First, we measured the height of water at 35 cm using a ruler.
The orifice with an 8 mm diameter was placed at the tip of the reservoir.
Turn on the hydraulic bench, then adjust the water speed and the adjustable overflow until the water fills the reservoir with height of 35 cm. When the water reaches 35 cm, make sure the water is in a controlled state without wave and remain at the same height until the reading is complete.
We set up the timer until it reached the height that we wanted.
Next, the distance between the probe sticks is measured and recorded. Next, to get the data, we adjusted the tips of the probe to be just in contact with the water jet.
Then we recorded the tip of the probe profile on the graph paper.
At first, we measured the height of water, 25 cm, by using a ruler.
The hydraulic bench was turned on, then the water speed and adjustable overflow were adjusted until the water filled the reservoir to a height of 25 cm. We set up the timer until it reached the height that we wanted.
We readjusted the position of the probe according to the water flowing out.
New reading for the height of the tip of probe profile will obtain due to change of the height of water. The vertical distance was marked and recorded.
Experiment will obtain the discharge velocity and contraction coefficient for two orifice sizes at two water head. For the 0.004 meter orifice at 0.35 meter head, we measure CD equals to 11.32, CV equals to 0.82, and CC equals to 0.07. With the same orifice at 0.25 meter head, the value increased to CD equals to 16.08, CV equals to 0.89, and CC equals to 0.06. In comparison, the 0.008 meter orifice at 0.35 meter gives CD equals to 3.43, CV equals to 0.75, CC equals to 0.22, while at 0.25 meter head, we found CD equals to 4.31, CV equals to 0.79, CC equals to 0.18. These results show that the smaller orifice consistently produce higher CD and CV, but lower CC, meaning the water exited faster and more efficiently, yet contracted more sharply. Additionally, reducing the head from 0.35 meter to 0.25 meter increased CD and CV, confirming that although a lower head reduces pressure, in this setup it boosts the discharge and velocity coefficient. We successfully measured the coefficient of discharge, velocity, and contraction for two orifice sizes under different heads. The results show that smaller orifice and higher water head produce greater CD and CV, which indicate faster, more efficient flow, while CC decrease, showing a sharper jet contraction. By tracking the jet trajectory and applying Bernoulli's principle with this real-world correction, we accurately determine actual flow rates. Overall, the experiment fulfilled all objectives and show how orifice size and water head influence fluid behavior in practical application.